Okay, so I'm going to walk you through the calculation of the performance for a turbojet. This problem is found in exam 2, which is a part of the air breathing propulsion module in A339. This problem is from when I took this class. I will give you a second now to pause the video and read the problem statement. Okay, so hopefully you've read the problem statement. I will be referring to the schematic here on the right, as well as the station numbering convention. I got this figure from the Hill and Peterson textbook that is used in this class. In this problem, we are asked to calculate the stagnation properties across each component, as well as determining the static temperature at the nozzle exit. In part B, we are asked to calculate the specific thrust and the thrust-specific fuel consumption. To begin, let's calculate the free stream stagnation properties, since we are not provided with that information. What we are provided with is the free stream Mach number, as well as the free stream temperature and pressure, and gamma, which is our specific heat ratio, which we're assuming is constant throughout the engine for the sake of simplicity. However, this is not the case in real life, and it varies. We will use the isentropic relations to determine the free stream stagnation properties. If you are unfamiliar with the isentropic relations, I would recommend reviewing them for Module 1, but you will be provided with these equations on the exam. So we have all the information here, and using this, we determine our free stream temperature to be a stagnation temperature to be 327.12 Kelvin, and our free stream stagnation pressure to be 0.1524 megapascal. Okay, so moving on to our diffuser. At the inlet of the diffuser, the stagnation properties are the same as the stagnation properties in the free stream, right here. So we will write that down. In this case, the temperature is 327.12 Kelvin, and the pressure is 0.1524 megapascals. In this case, we are provided the pressure ratio across the diffuser to be 0.92, which means that there is an 8% pressure loss across the diffuser. The second point is that we're going to assume the diffuser to be adiabatic, which means that the stagnation pressure is constant throughout the diffuser. In this case, at the diffuser exit / the compressor inlet, the stagnation temperature is going to be 327.12 Kelvin. And to determine the stagnation pressure, we just multiply the pressure ratio by the stagnation pressure at the diffuser inlet. And when we do that, we determine it to be 0.1402 megapascal. Okay, so moving on to the compressor. We are given the pressure ratio across the compressor as well as the efficiency. Gamma is once again constant. To determine the stagnation pressure at the compressor exit, so I'll just label these real quick. So this is 1, this is 2, this is 3 at the compressor exit, station 3. We simply have to multiply the pressure ratio by the stagnation pressure at the compressor inlet. And when we do that, we determine the stagnation pressure to be 2.8048. So that's just multiplied by 20, right? To determine the stagnation temperature at the compressor exit, there are 2 sub-steps. In the first sub-step, we are going to determine the isentropic stagnation temperature using the isentropic relation, just like before. Then we can use this quantity, which we determined to be 769.89 Kelvin, in our compressor efficiency equation to determine our actual temperature at the compressor exit. And when we solve for this simple algebraic equation, we determine this to be slightly higher than the isentropic at 830.27 Kelvin. Moving on to the combustor, we are given the pressure ratio across the combustor as well as the turbine inlet / combustor exit temperature. The fuel heating value and gamma is still constant. To determine the stagnation pressure, we simply have to multiply the pressure ratio by the stagnation pressure at the inlet of the combustor. And when we do that, we determine the stagnation pressure at the turbine inlet to be 2.7487 megapascal. And the stagnation temperature, well, the turbine inlet temperature were given to us, so that's just 1800. So we just write that down. This is the easy part. The second part of this particular section in the combustor is determining the fuel-air ratio. Even though we're not asked to tabulate this, we need this information to solve for the next part of the problem. So the fuel-air ratio is simply the mass flow rate of the fuel to the mass flow rate of the air. You won't be given this equation on your equation sheet, but you can solve for this by doing an energy balance and deriving it that way. The energy balance, the idea behind it is that energy into the system equals the energy that coming out of the system, right? The system in this case is our combustor. So we're going to write this mathematically in terms of the enthalpy. So the stagnation enthalpy at the exit of the combustor / turbine inlet equals the enthalpy at the combustor inlet plus the enthalpy associated with the addition of our fuel. So writing out the enthalpy, this is basically equal to the mass flow rate, the sum of the mass flow rate in this case for H04, since we are adding fuel here after the combustor or in the combustor, times Cp, which you can determine from the value gamma and the gas constant times the turbine inlet temperature. And this again equals the mass flow rate of the air at the inlet of the combustor. We're not accounting for our fuel here since we haven't added it yet, times Cp once again, and the stagnation temperature at the combustor inlet. And then we also write down the enthalpy that's associated with our fuel, which is just the mass flow rate of the fuel times the fuel heating value. And when we divide both sides by the mass flow rate of the air, we get this ratio again, which is simply our value F. And we do a little bit of algebra there to solve for F. And you'll end up with this equation. And we know all of the values here. So we can calculate our fuel to air ratio to be 0.0254. So this makes sense because since this is an air-breathing engine, the engine uses less fuel in comparison to the amount of air it uses. Okay, coming to the turbine, the only information that we are given is the turbine efficiency of 0.85. To determine the stagnation temperature at the turbine exit, we first need to understand what the turbine does in a turbojet. The power that's extracted by the turbine is from the hot combustion gases from the combustor is used to drive the compressor, which further drives the cycle. This means that the power that's output by the turbine equals the negative of the power that's consumed by the compressor. And this is yet again another energy balance. So using the same principles of performing an energy balance like before, the only difference is we're going to apply it just to the turbine section here and the compressor section here, respectively, right? So that's why we take this difference in the stagnation temperatures. We can solve for this and we get this equation, and we can solve for the actual stagnation temperature at the turbine exit this way. And this is where that fuel to air ratio that we determined earlier makes a play. And we determine the stagnation temperature to be, at the turbine exit, 1309.31 Kelvin. To calculate the stagnation pressure at the turbine exit, we first need to determine the isentropic stagnation temperature, which we can calculate from the turbine efficiency since we are provided that. So solving for the simple algebraic equation, we determine the isentropic stagnation temperature to be 1222 Kelvin roughly, and we can then use this in our isentropic relations from before, right? We need to use our isentropic temperature for this. So we can use this in the isentropic relations to solve for the stagnation pressure at the exit, and we determine that to be 0.709 megapascal. Okay, moving on to the nozzle. We are given the nozzle efficiency as well as the static pressure at the nozzle exit. Note that this engine does not use an afterburner, so we are going directly from station 5 to station 7. We are going to assume that the nozzle is adiabatic, just like our diffuser. That means that the stagnation temperature is constant across the nozzle. To determine the isentropic static temperature, we will need this to solve for the static temperature, which is what we are asked for right here. We first need to determine the isentropic static temperature, so we will do this by applying our isentropic relations using our stagnation property at the inlet to the nozzle and our static properties at the exit of the nozzle. And then solving for the static temperature, we find it to be 748.17 Kelvin. And then we can use this in our nozzle efficiency equation, right there. And we can then solve for T sub 7. And when we solve for it, we determine that to be 770.62 Kelvin, right? Moving on, to calculate the stagnation pressure, we can once again use our isentropic relations, and we can use the T sub 7 that we just used. So we apply the isentropic relation this time to the exit plane of the nozzle, right? The same thing, we're going to use the stagnation property as well as the static property at the exit plane of the nozzle, and we can solve for the stagnation pressure here, and we find that to be 0.639 megapascal. So the isentropic relations are very versatile, and that's why it's important that we understand that to solve this problem. Finally, we will solve for the exhaust gas speed, and to do this, we're going to apply yet again another energy balance, this time to the exit plane of the nozzle. Since the mass flow rate here is constant, we're going to work with the specific stagnation enthalpy this time. So this is analogous to the total energy being the sum of the potential energy as well as the kinetic energy, right? So we know all of these quantities, so we can solve for our exhaust gas speed, and we determine that to be 1040.28 meters per second. Okay, now we have solved part A. We're going to move on to part B. At this point, we have all the information that we need to determine the specific thrust, as well as the thrust-specific fuel consumption of this engine. So to begin with, the specific thrust, this is basically equal to 1 plus the fuel-to-air ratio, the whole thing times the exhaust gas speed, and we're going to subtract the free stream airspeed from this. And this, since we're given our Mach number as well as we can determine the speed of sound, we determine this speed to be 272.5 meters per second. And plugging this number in here, we can calculate that our specific thrust is 793.62 meters per second. So if we multiply this with the mass flow rate of our air, we can determine the thrust that is produced by this engine. The thrust-specific fuel consumption is basically how much fuel the engine is consuming per unit of thrust that it produces. So it's literally the mass flow rate of the fuel to the thrust that's produced by the engine. And if you work this out, this simplifies to the fuel-to-air ratio by the specific thrust. So when you plug all of these numbers in and solve for it, we find that the thrust-specific fuel consumption for this particular engine is 3.2 times 10 to the negative 5 kilograms per second of fuel per unit of thrust that it produces. That's the end of this problem. I hope that you find this useful.